Hey Lane, can you hear me?
Yep, I can hear you.
Excellent. Just you and me so far.
Okay.
Nobody's here in North Platte yet.
Hmm.
But
I joined just like a second before you got on.
well, we'll see who else shows up.
How are you doing today?
I'm well, and yourself?
I'm all right. I almost overslept because I didn't have my other class that I usually get up at around 7:04.
Well, I woke up at around 3:45,
Oh boy.
went back to sleep for another hour, got up, showered, and started working on my homework assignment for my advanced statistics course, which is not going well. Can't
Oh
figure,
boy.
can't figure out this stupid code for statistics.
Oh,
But we'll get there eventually.
yeah. We should get it figured out soon.
Thank you. I have about 14 hours.
Oh yeah, that's plenty of time.
Yeah, considering I've spent about 70 hours on it, maybe not.
Mm.
Very long homework assignment. I think I'm spending far too much time doing it than I should, but whatever. Let's see here. What are we doing today?
I think you were wanting to look over chapter 10 again for a little bit.
This chapter 10. Do we have an exam this week? Calendar.
Yeah, Wednesday, according to
All right. So chapter 10 is due today. We'll answer any questions anybody has, and then we'll move on to chapter 11. Let's fix some things while we're here, while we're sitting here. Let's make this one chapter 11. That's not electromagnetic waves. What is chapter 11? Chapter 11 is magnetic forces and fields. Copy. Um, Underline it, bold it, make it bigger. Hmm. Calendar. So that's chapter 11. Oh, gotta fix that again.
geez, did everyone else assume you had no class today?
I have no idea. I have no idea. But they're not here yet. So, what is going on with this dumb thing? Oh, that's the problem. That'll be chapter 11. Yes. Okay. Let's save that. Chapter 12. What's chapter 12 all about? Chapter 12 has got to be more magnetism, sources of magnetic fields. That in here. We'll give them a few more minutes and then we'll move on. And this will be chapter 12. And we'll do one more and then we'll go ahead and start. That chapter. Okay, so going back to our calendar, let's go ahead and look at some things here. First of all, let's share screen with you. Okay, so our calendar. So we're going to have chapter 11. We're going to get done this week. Chapter 12 will be next week. Chapter 13 the following week. We have technically 16 chapters, but we don't necessarily have to cover all of them. It goes all the way to waves, and it actually covers, there are two chapters that cover, or two or three chapters that cover pretty much all the same thing. But we'll try to get to, let's see, let's look at the book really quick here. Here we go. So we'll get to we should get all the way to chapter 14 without any troubles, and hopefully chapter 15 as well.
Before the end of the semester.
Yeah. If we get to chapter 14, we will be we really should get to chapter 15, honestly. Don't do a lot of things in chapter 16. So we'll try to get to chapter 15. That means today. So this week, if we go to chapter 11 is not terribly difficult. It's probably the easiest of these last few chapters. Chapter 12, also not a hugely difficult one. Although Ampere's law has a little bit of calculus involved. There's calculus involved everywhere, but nothing that we really need to do calculations with. In most of these chapters, we're going to be just using calculus to create formulas, and then we'll be using formulas. So it's not that big a deal. That's definitely the case with chapter 13. The only chapter 12 is one where we'll use a little bit of calculus in our in our actual homework, I think. But the rest, most of the rest of this, most of the rest of these chapters are about figuring out the formulas in class together and then just turning you loose on homework using formulas and going from there. And that is until we get to the circuits with inductance. Those get a little more challenging, but those are right at the end there, but not too bad. We're in the home stretch. So do you have any questions about chapter 10 homework before we move on to chapter 11?
Not really.
Not really, okay. Well, if that's the case, then let's go ahead and start chapter 11. It's too bad that nobody else is here, but that's just tough luck. We gotta move on. So chapter 11, here we go. Chapter 11, all about magnetism. So magnetism is something that has been discovered, it was discovered a long time ago, just by discovering certain rocks were magnetic. They attracted other rocks. Right? So particularly these rocks that tended to have these properties were definitely metallic. And the way that people discovered, knew that things were metallic back in the day was pretty much by just they were shiny, metallic things were shiny and a little bit more dense, a little heavier than other rocks. But magnetism has been used also by people to do things for a very long time as well, even if the science of the magnetism itself wasn't very well understood. One of the things that was discovered a fairly long time ago is that if you have a magnetic piece of material and you have it in a situation where it can rotate, if it's balanced on a point or if it's sitting on a floating piece of wood in water that's calm water, if you've got that kind of a situation where the magnetic rock or magnetic material can easily rotate and you're on the earth, that most of these things tend to point in a specific direction. And this was, excuse me, this was something that was used to advantage, because if you have a rock that always points in the same direction and you're out there wandering around in the wilderness, that rock can help you to find where you are going, where you have come from. It helps you to kind of keep oriented because you always know this one particular direction. And of course, nowadays we call that direction north, which is kind of funny actually, but we call it north, and we've now have some understanding of why this phenomenon occurs. And the reason, of course, is that the rocks have these magnetic quality to them. And the earth also has this similar magnetic quality to it. So here is a map of what the earth would look like if it was a magnet. It would look like a big magnet with the south pole of the magnet at the north pole of the earth. The north pole of the earth is actually the magnetic south pole of the earth, and that's why it's kind of funny. But all magnets have poles, it turns out. And this is one really mysterious thing about magnets. Remember when we were dealing with electrical charges, there were two types of charge, and you could have two kinds of charge in one thing. Atoms have both positive and negative charges. But you can also have ionized atoms that have only positive charges. You can take all the electrons off and take them away and have just positive charges on your atom. And so positive charges and negative charges can exist separately from each other in nature as far as we observe. But in magnets, that's not true. Magnets always have to have at least a north and a south pole there has to be a south pole for every north pole, right? They have to have this feature. It's always the case. Even when there's no physical north or south pole to a magnet, because sometimes that is the case, even when that is the case, it still must behave as if it has a north and south pole. The magnetic field still must behave as if those poles are there. And so that's kind of a weird mystery. We're not sure why that is. There's a lot of theories about it, but we're not sure why it is. So magnetism is a bit weird. And the Earth is not any exception to that weirdness. It has a north and a south pole. Even if you cut a magnet in half, you will get two magnets, each with a north and a south pole, instead of getting, a north pole magnet and a south pole magnet. It'll just create new poles. Anyway, the point is that on the Earth, when you put a magnet out here, like this little compass that they put here, or this little compass they put over here, or this little compass they put down here, these are all magnets. When you put a magnet in a field of another magnet, and these lines represent the field of the magnet of the Earth, then the North Pole will align itself so that it's pointing in the direction of the field. Here's the arrow point that indicates the direction of the field. And the South Pole will point in the opposite of the direction of that field. And the reason for that is partly convention. We have decided that magnetic fields will go out of the North Pole of a magnet, so that it's coming out here, and then it always goes around, it always loops around, it always curves, and then it comes back into the South Pole of the magnet, and it connects to the field line inside the magnet somewhere, going to the one that was going out. So all these field lines are loops that connect back to themselves. And that is always the case with magnetic fields. Magnetic field lines are always loops that connect to themselves. And you can have loops within loops, like you can see here, there's smaller loops within these bigger loops. And the distance between the loops, or the distance between the field lines, still indicates how strong the field is. So you can see that at the North Pole, the field is much stronger because the field lines are closer together. But at the equator, the field lines are quite far apart, so that's where the field is the weakest. It's always pointing towards the North Pole, though, if you're out here on the Earth's surface somewhere. Unless you're at the North Pole or close to it, then those field lines are pointing straight into the ground. So at the North Pole, right at this point where these field lines come in, right at this point where these field lines come in, and the same thing on the South Pole, your compass doesn't work very well there because it doesn't line up with the field if you hold it flat parallel to the surface. It will line up with the field if you turn it on its end, and then the North Pole of your compass will actually point straight down to the ground, because this is the way it's going down in here. And on the South Pole, the North Pole of the compass will point straight up at where those field lines go into the ground. And we'll learn more about what happens on the Earth as these field lines go into the ground, but that's basically the idea here. And so these things have been discovered, have been around for a long time, and people have figured out kind of their usefulness for a very long time. Now we've started to do a lot more with magnets in the years since. Here, this is the read-write head of a hard drive, which of course is not something that we're using as much anymore in computers or cell phones or anything. But it used to be that you would have to magnetically store the memory of your computer on a magnetic disk. So this disk here is made of an alloy of metals that can become magnetic when you bring a magnet close to it. And then these little probes here that go in between the disks and on top of the disk would magnetize different little regions of the disk. And the pattern of magnetization was a digital code for the data that you had stored on the disk. And you could make very tiny little patterns so that you could store a lot of data. So that's what hard drives are all about. Hard drives, the memory in your computer is not on a hard drive at all anymore. Now they call it a solid state hard drive, SHD or SSD or an SHD or whatever they call it. But it's actually just a bunch of computer chips that the memory is stored in. So we've come a long way with computer chip technology, and flash memory that's what flash memory is, and other kinds of digital or solid state memory is.
With solid state, doesn't just hold a bunch of individual like charges?
Solid state. So when the word solid state refers to a atomic state in the atoms in the material. And so when you're storing data in a solid state device, which is what microchips are, you're actually storing data in the atomic state of those atoms. You're essentially manipulating the atoms to store it. Now, if you want to think of the energy states in an atom as electrical states, which technically they are, because it's the energy of the electrons. It's where it's the arrangement of the electrons in the atom. You could think of it as it's one way to. So then you could say, oh yeah, then there's some kind of charge that is you're manipulating the charge in some way to represent a piece of data. However, in solid state devices, it's not literally charge. Well, not in all solid state devices. In some solid state devices, it kind of is. But in any way, the point is that in memory on your computer, like solid state memory, it's actually an atomic state or a quantum storage state, a quantum arrangement. Or describing quantum mechanics is very difficult without using quantum terminology. And quantum terminology is something you have not learned yet. So, but the point is that it has something to do with changing the actual state of the material, and then that state represents digital information. Those states represent individual information. So if you think in a very simplistic way, yeah, it has something to do with charge and discharge. But in a
It's like almost, it's just, you're saying it's essentially just changing the properties of material inside the drive. Okay.
Yeah, it's changing something about the solid. It's changing something about the quantum arrangement, you could think of it as. And that is oversimplifying it dramatically. But if you go on to study more physics, that will make more sense to you as you learn more about atoms, essentially. The quantum theory and quantum mechanics is more subtle than people make it seem. So anyway, it just has to do with something. Like if it was just plain charge on those chips, then the charge would either drain off or could easily be pulled off by turning off the computer and just having the computer in the world, just existing in nature. That memory would be lost. But because it's a little bit more than that, it's a little bit different than that, than just charge. That memory that's on your computer is it's very secure. It's not going to be affected by the world around it very easily. So, and that's the beauty of solid state memory, is that it is very unaffected by the world around it. The hard drives in older computers they could be affected by the Earth's magnetic field, and so they had to be shielded very carefully, and they had to take a lot of precautions to make sure that nothing magnetic came close to the computer. You could erase a computer by bringing a strong magnet next to it. It was quite easy to do that with old computers. And it happened a lot to people. People would put their computer in a laboratory near a magnet, and it would destroy the memory on the computer. I mean, the beauty of magnetic fields, one of the great things about magnetic fields is that they drop off very quickly. So if you have a strong magnetic field, even a super strong magnetic field, and you move away from it just a short distance, it actually, the magnetic field drops in strength really dramatically. But when you're very close to them, it still that full effect can cause damage to computers and all kinds of things. So anyway, it's all very yeah. It's a moot point at this point in technology, because we hardly use hard drives. They're magnetic anymore, but it still is quite interesting. We had to deal with that a lot when I was growing up in computers. So what is the magnetic field? Well, the magnetic field is going to be defined by any other field, by force that is observed. So the magnetic field exerts forces on things. But the magnetic field, again, is weird. Everything about the magnetic field is weird. And so it turns out that magnetic fields exert forces on charges, on electrical charges. Well, we weren't expecting that, maybe. And the way that the magnetic field exerts forces on charges is really strange. A magnetic field will only cause a charge to move or exert a force on a charge if something is changing. So one of the things that can be changing in the system is the charge's position can be changing. If the charge is moving through the magnetic field, everything else is staying the same except the charge is moving, then the charge might feel a force from the magnetic field. But it's even weirder than that. It depends on which direction the charge is moving relative to the direction of the magnetic field. So let's imagine that we have a magnetic field that is pointing in a particular direction. Here is a piece of glass that has a magnet, and in the plane of the piece of glass, they're calling this the VB plane, the velocity magnetic field plane. In the plane where this piece of glass is sitting, there's a magnetic field that is pointing out of the page here. So it's coming straight at us. It looks like it's not, but it is. And then also in this plane of the glass, there is a charge moving to the left. So you can see that green arrow represents the velocity of the charge. If this is the case, if you have a magnetic field that's coming out of the page and a charge is moving to the left in that magnetic field, that charge will actually feel a force straight upward. Now that's weird, right? And it is weird, it's very weird, but it is also true. This is something that we have observed gazillions of times, and it always works out this way. We've never seen it behave any differently. We can actually use a right-hand rule to determine the direction that a charge is going to be pushed in a magnetic field. And the right-hand rule that we use is we put our hand like the karate chop motion hand, right? And we chop our finger in the direction that the electric charge is moving. So we chop our hand in the direction of the velocity, which is to the left, right? I don't know which way you're seeing my hand move, but and then what you'll do is you'll turn your fingers, you'll turn your fingers in the direction that the magnetic field is pointing. And to do that, you might have to rotate your hand. So if the velocity is going this way and the magnetic field is coming towards my face, then I can just turn the fingers towards my face. But if they're going away from my face, I might have to rotate my hand and do that. But whatever you have to do to get your fingers so that they can turn in the direction of the magnetic field, you do that. And then once you've done that, whichever way your thumb is pointing, will tell you which the force that it's feeling. So in this case, we have our hand going to the left, our magnetic field coming out of the page, which is towards my face. And that means the magnetic field is going to be pointing, or sorry, the magnetic force on the electric charge is going to be pointing up. Now, this is only true, however, for a positive charge. So for a positive charge, we use this right-hand rule. Velocity of the charge, magnetic field, turn your fingers, thumb will point in the direction of the force on that charge. However, if it's a negative charge, the right-hand rule will tell you the direction, the wrong direction. And it'll tell you exactly the opposite wrong direction, right? So if it's an electron moving in this field, it's a negative charge, then you do the right-hand rule, karate chop your hand in the direction of velocity, turn your fingers in the direction of the magnetic field out of the page. And then you say, oh, wait, but it's an electron. So I actually am going to feel a force downward because my thumb's pointing upward. So you have to be aware of that. You have to keep track of that. And there's one other weird thing about this. If this charge feels a force, a magnetic force on it, all of a sudden it's going to change its velocity then, right? So it will no longer be going to the left. If it feels a force upward, it will be going to the left and upward after it feels this force. So now we've changed the velocity and it looks like it's going, instead of to the left, it's going to the left and slightly upward like this. I should do that in a different color. That's not as green as that one, but anyway, it's good enough. So now it's going to the left and upward a little bit. And so then you have to do it again. So you karate chop your hand left and upward a little bit. and the magnetic field is still pointing out of the page, so we do that. But now the force is actually not upward, but it's upward and to the right. It's this way. And if you do it again, it of course is feeling a force again. That means it's pushed it upward some more. And so the next time you do this, in the very next moment, it's this way. And what happens to this charge that's moving along, right? Originally, this charge was moving along kind of like, let me see if I can.
It's like its path is almost circular.
Yeah, it actually starts to go into a loop. It goes into a circle, exactly. So you start off with your charge here, and then it's here. Whoops, that's not color I want this color. Then it's here, and then it's here, and then it's here, and then it's here, and eventually it'll actually come back to where it started. This is not a very good circle. And then it'll essentially go into a circle as long as this magnetic field is pointing the same direction along its entire path. So charges that enter magnetic fields in straight lines end up going around in circles in that magnetic field if the magnetic field is strong enough to pull it into a circle within the area that the magnetic field exists. Right? If the magnetic field only exists for a meter or so, it might just turn this into a path. It might just turn it into a path and then it goes off at a different angle after it leaves the magnetic field. But if the magnetic field region is big enough, it'll end up going into circles if that magnetic field is pointing the same direction everywhere and at the same strength everywhere. And of course, positive charges will go into these circles that go upward in this particular field, and negative charges will go downward in this field. So if you have multiple charges, you'll get multiple circles. And it'll also depend on the mass of the charge. If the charge has a bigger mass, then it's going to be harder for the magnetic force to turn it. So it'll make a bigger circle. If it's a smaller mass, it'll be easier for the force to turn it. So it'll be tighter circles. But it also depends on the speed of the mass. If the mass is going super fast, it's not going to turn it as quickly, and so it's going to make bigger circles. If the mass is going slowly, the force is going to have a bigger effect, and it's going to turn it in tighter circles. So it's a very complex thing, and it's very weird.
Wouldn't it, if it goes fast enough, just ignore the magnetic field and keep going past it?
It wouldn't ignore it entirely. It would just get turned a little bit, kind of like this one that just got turned and then went on its way, right?
Yeah, just kept going.
Yeah, because how fast it's going also determines how much force it feels. So there's an interplay. If you're going faster, you actually feel more force, but you also get turned less. So it's a very complex thing. And it's a very weird thing. Why would moving faster make the force bigger? Because magnetic field forces depend on change. Something is changing, and if something is changing more, the force increases. If something is changing less, then the force decreases. Now, this is just one way that this can change. That's just one way that this system can change and create a force on this system. But it can also, if the magnetic field changes while the charge is in this region, the charge can just be sitting there doing nothing. And if the magnetic field changes, it can actually apply a force to the charge. But we're not going to talk about that situation until later. So anyway, this is the weirdness. This is your first introduction to the weirdness of magnetism. It is a very weird thing. And this is how we define the magnetic field. We actually just send it. If we want to know how much magnetic field there is in a region, the way that we figure it out is we move charges through the region. We shoot charges through the region and see how much they turn. And because we put the charges through, we know how fast they're going. We know what their mass is. We know what their charge is. We know all the information except how much force they're going to feel, how much they're going to turn. And we observe how much they turn. We calculate that force. And then we can use this right-hand rule to figure out which way the magnetic field was pointing. And then we can also calculate it using a formula, which we're about to learn. So here they do a bunch of exercises where you use that right-hand rule to figure out which way particles are going to turn in a magnetic field. And I highly recommend you practice these. So let's practice them right now. Get your right hand out. And we're going to say, okay, we karate chop in the direction of the the velocities. In this case, my velocity is coming out of the screen, so I'm going to point that towards my face. And then we turn our fingers in the direction of the magnetic field. And I'm going to have to rotate my hand this way because the magnetic field's up so that I can turn my fingers up. You see that? And that means the force is going to be off to the left there, which is correct right there. And then this one, the velocity is to the left. So I karate chop to the left. And I need to rotate my hand so my palm is upward so I can turn my fingers upward to the magnetic field. And that means the force is going to be into the page, which is correct. And here we have an interesting one. We have the velocity up, and a karate chop up, and the magnetic field is up. And I can't turn my hand in any way so that I can turn my fingers up. So what is the force in this situation?
Is it kind of just all around, or?
It's actually zero. And that's actually an interesting answer because all around would be true if you said all around so that it cancels out, right? Because that would actually be a very good answer if you just include that all around it so that it cancels out, because that actually kind of philosophically makes sense.
If it's being pulled in every direction all at once, it's kind of like not really.
Yeah.
If it's assuming it's all the same force, and okay, yeah.
Yeah. So and that we don't really have a way of measuring that, but theoretically, that's a really good thought, right? But anyway, the point is that if you have a charge that's moving in the same direction of the magnetic field, and it also works if the charge is moving in the opposite direction of the magnetic field. So if the charge is essentially following the magnetic field or going upstream in the magnetic field, it doesn't feel any force. It's not affected by the magnetic field in that case. And that's quite interesting. And then you have a situation where it's kind of off kilter here, where we have a velocity kind of going downward to the left, the magnetic field going straight up. Well, I can rotate my hand to turn my finger straight up. And that means that the force is going off here in this angle somewhere in this direction. But that definitely is going to feel some kind of force. So that is another situation. And they do a lot of, we're doing a lot of this stuff in the homework in the book. Now, another thing, one of the things about this right-hand rule is that when there's a right-hand rule involved, we know that mathematically that represents a cross product. We've been there before, right? And so it turns out that the force that is felt by a charge moving through a magnetic field is equal to the amount of charge of the charge moving, the velocity of the charge moving, and then you take that cross product with the magnetic field, and then you will get the value for the force. Now, if you don't remember what the cross product is or how to calculate it, then you got to go all the way back to chapter 1 and chapter 2 on vectors and math. No, chapter 2 on vectors and math. And do that. We're gonna show you cross products in this chapter, but it'd be a good idea to go back and review and do some practice there. But we're definitely going to be dealing with a cross product. That right-hand rule is indicative of the cross product. If you have right angle, well, if you know the angle between, it doesn't have to be right angles, but if you know the angle between the velocity and the magnetic field, then you can use this shorthand formula to calculate the magnitude of the magnetic force. Q times V times the magnetic field times sine of theta, where everything here is magnitudes instead of vectors. This is only going to tell you how much force it feels, not which direction it is. Well, if you know those angles, then you can draw the picture and do the right-hand rule and figure out which direction it's going to be in. It may not tell you exactly the direction, but it'll tell you approximately the direction. We also know from cross products that whenever you have a cross product that creates a new vector, that new vector is 90 degrees to both of these vectors. It's at a 90-degree angle to both of these vectors. So that helps us to figure out which angle it's pointing. You figure out what plane these vectors are in, and this one is going to be perpendicular to the plane. So if these two vectors are in the XY plane, then this vector is going to be in the Z plane, either positive or negative Z. Right, for sure. If these are in the YZ plane, then this is definitely going to be in the X direction. If this is in the XZ plane, this is definitely going to be in the Y direction, either positive or negative. So if you know which plane these two are in, you can figure out what direction this one is, either positive or negative. And then use the right-hand rule to figure that out. And since all vectors, when all vectors cross, and that's what a cross product is, whenever two vectors cross, they create a plane. So you might as well put them in one of the three cardinal planes, the XY plane, the XZ plane, or the YZ plane. And then you know which direction the force is pointing. It's pointing in one of the cardinal directions, depending on the right-hand rule. So anyway, magnetic fields are measured in Teslas, and Teslas are measured in newtons per amp meter. We'll figure out why amps are involved here later, why current is part of the Tesla. And of course, this is named after Nikola Tesla, a very famous inventor and scientist of the early 20th century. Mostly an inventor, but anyway. We also use a smaller unit called the Gauss, because 1 Tesla of magnetic field is a huge amount of magnetic field. And Gauss is much closer to the magnetic fields that we experience on Earth. For example, Earth's magnetic field is about 10 to the minus 5th Tesla, but it's only half a Gauss. So it's a very small amount of Teslas, but it's about 1 Gaussish, about a half a Gauss. So that makes more sense for the magnetic fields that we deal with. Here's just a little method for there. That's the explanation of the right-hand rule method. Let's see. So let's do this problem. So we've already looked at these different scenarios with the right-hand rule. Let's actually look at the math. In the math, they tell us the charge, that's an alpha particle that has this amount of charge and it's positive. They tell us the magnetic field is uniform of 1.5 Tesla. No. Yeah, they're using a magnetic field that's quite strong, 1.5 Tesla. And they tell us which direction the magnetic field is pointing in. It is parallel to the x-axis, so it's moving in the direction of the z-axis. It's moving in the direction of z. And so we can plot it out here, which is what they've done. And then they tell us the different directions of the alpha particle can move. In part A, they have it moving in the negative. In part A, they have it moving in the positive x direction. In part B, they have it moving in the negative y direction. In part C, they have it moving in the positive z direction. And then in part D, they have it moving in some direction between the x and y axes, or in the xy plane somewhere. And they define that, actually it's in the xyz plane. So it's actually just a vector just out there in space. 2 I hat minus 3 j hat plus 1 k hat times 10 to the 4 meters per second. So that velocity vector is much more complicated. All the rest of these are just, I hat or j hat or k hat. This one has all 3 components. So this one here is going to involve some more complex math. The angle between the velocity and the magnetic field here is 90 degrees. So we know that angle. Between here and here, it's 90 degrees. Between here and here, it's 0 degrees. So we can use that formula for the magnitude of the magnetic force quite easily in parts A, B, and C, which is what we expect them to do. Although they actually do use the cross product here, which is going to result in a very simple answer. I hat crossed with j hat always gives you 1 because it's 90 degrees between it. And it always gives you, I hat crossed with k hat always gives you negative j hat. And that, knowing that comes from chapter 2. You got to go back to chapter 2 and look at different cross products. But if you cross I with j and they're both positive vectors, which these are both positive vectors, it'll always, I with k, I think I said j, but anyway, if you cross I with k and they're both positive, you'll always get negative j. And so this answer right here is this number times this number with a negative sign in front of it. And that's the answer. And then you put the j hat there. It turns out that if you cross j with k and they're both positive numbers, you always get negative I. And so this number times this number gives us this number, and then we plug the negative in front of it and put the I hat on it. And then the third one, C, since there's a 0 degree angle between them, then the cross product between two angles that are in the same direction, in this case, they're both in the z hat direction, so k hat cross k hat is equal to 0, and it just gives us a 0 force. Now this one's a little more complicated. Our velocity vector here's our Q, here's our velocity vector. It has all three components in it. It has an I hat component, a J hat component, a K hat component. The magnetic field is just K hat component. So doing this cross product here is going to be a little more complicated. You can do it a couple of different ways. One way you can do it is just calculate the magnitude. And that's what they're going to do here. They're going to calculate the magnitude of it by using the Pythagorean theorem. And when they do that, oh, they don't actually do that. No, sorry. So no, they actually do calculate this cross product in terms of the components first. So the solution to this cross product is actually negative 14.4 I hat minus 9.6 J hat, which may not make sense at first, but we'll show you how that's done here in a second, if you don't remember. And then it's times 10 to the minus 15, of course, because the 10 to the minus 4 and the 10 to the minus 19 get multiplied together. And then the units are just newtons because we're calculating force. But this answer can be written just like this. This can be your answer if they're asking for it in component form. Or you can write it out as a magnitude by using the Pythagorean theorem here. So the magnitude of this vector is negative 14.4 squared plus negative 9.6 squared. Take the square root, then you got that, and times 10 to the minus 15 square root as well. And which is funny because they don't actually write the 10 to the negative 15s in here, and they should have. And they should have taken the square root of that as well, which they didn't. But they did a shortcut here. So the shortcut that they did is they said, oh, if we put 10 to the minus 15 here and squared, and 10 to the minus 15 here and squared, we're going to get 10 to the 30 on each of these. And then we'll take the square root of 10 to the 30 and get 10 to the 15. So they just put it out the outside as 10 to the 15. They skipped the squaring and the square rooting of the 10 to the minus, but whatever. In the end, the answer is correct, and that is the magnitude of this force. And then they take the y component over the x component, take its inverse tangent, and that gives you the angle theta from the x-axis for that. So that is another way you can represent that, the magnitude and the angle from the x-axis, the positive x-axis. So they also use the magnitude of the velocity and the magnitude of the force to calculate the magnitude of the force, which you can do using the original equation, gives you the same answer for the magnitude of the force. But let's go back to chapter 2 really quick and look at how this, oh shoot. We have to go to chapter 2 of volume 1 of this book. So we got to go find volume 1 of the book. Let's go find volume 1. That didn't work. There we go. And let's go to okay, so University Physics, Volume 1, Chapter 2. Vectors. So we're going to go to the product of vectors page here. And they do the dot product first, and then they do the cross product later on, which they call the vector product, the cross product, right? So they go through all this stuff about, you know, this is the magnitude of the vector, which we just talked about. But how do we actually do this calculation? So the way that they actually work out this calculation is just by using kind of the FOIL method, first outside, inside, last, but with vectors and with vector components. And so this is where they're doing this. This is where they're doing this kind of FOIL method-ish thing. And the results of it are right here. So in the results of the FOIL method, A cross B, where A has 3 components and B has 3 components, then you do the first one here, multiplied by the first one here by the middle one here, first one here by the last one here, And then you do the second one by the first one, the second one by the second one, second one by the third one, and so on. You do this and you get all these terms and it looks really messy. But then you have all of these are cross products. Each one of these is a cross product. Well, when you get we know already that the cross product between I and I is going to be 0, and the cross product between J and J is going to be 0, and K is going to be 0. So you go through all these and you find all those ones that are I hat cross I hat, or J hat cross J hat, and K hat cross K hat, turn them into 0. Turns out that that's the stuff that's right here, here, and here. So it's this first one, this middle one, and this last one here are all going to go to 0. So that you get, those ones are they just get eliminated. Then you're left with 2 terms up here that have there's one where there's sorry, 2 terms up here, one where there's an I and a J crossed, here's an I and a K crossed, and then they have a J and an I crossed, then a J and a K, and so on and so forth. Well, we actually can figure out all those using the right-hand rule, and they do that right here. This is where, that's what they're doing right here, is figuring out what all the I, J's, and K's crossed together make. And then they replace those with their answers, which end up being negative J's or positive K's or negative K's or negative I's or positive I's, whatever. They replace all those, but then they still have all these components, all these are all the coefficients, essentially, the numbers that were in front of those unit vectors. So those are still present, and this is the result of all that multiplication. So you don't have to actually do that all over again. You can just look at this formula. If you have 2 vectors A and B that are a cross product with each other, then you take the first coefficient, the coefficient of the first component of A, and the coefficient of the second component of A, the Y component of A, and the Z component of B, multiply them together, and then you subtract the Z component of A and the Y component of B, and you do that arithmetic, and that'll give you a number, and then you multiply that by I hat. That's your I hat component. You do something similar, but with different components for the second part, the J hat component. Another thing that's similar, but uses different components for the K hat component. And then that will give you a vector that has some number times I hat, plus some number times J hat, plus some number times K hat, and you will be done with the cross product. And that's what they did in the first part of the example. In the first part of the example, they actually do this cross product directly using that formula, and they get this direct vector at the end. So, all right. And we're done for today. Actually, a little overtime, but got through one section almost, 2 sections. All right, way to go, us. All right, we'll come back on Wednesday and continue on with doing some more things with magnetic fields and charges, and then we'll learn about how you can make other kinds of magnetic fields and how you can detect them and everything else. So have a good day. We will see you later.
Yep. Have a good day.